Good morning, everybody. I'm running about a minute and a half late. I'll go an extra half hour today to make up for Dr. White being late. One of my bad habits is I try and squeeze too much in to a certain time period. And this morning I went shopping. I just finished cooking something I bought and I timed it really close. So I'll go an extra 5 minutes to make up for being late. Give everybody time to log in. I'm looking at how many people have logged in. Is everybody's running late like I am, or maybe they thought, oh no, he's not showing up today. Wrong. Again, I apologize for being late. All right, let's get started. If you've checked your email or do it after my class, you'll find out that I sent out about 8:30 this morning the email with the test number 2 password. And please take test number 2, download it from the assignment area in Blackboard. There's also a periodic table. There's also instructions how to take the test and make it into a PDF file. I have 2 ways now. If you don't have a scanner, you can use the app for your cell phone, or you can take pictures of your cell phone and use the method I have in there. I haven't tested the app, but I've been told it works quite well. If any of you do, let me know by email how it turned out. Speaking about turning out, once again, Dr. White had fun with Labster. And I'll ask, could someone email me where they found the gas laws Labster? Because I couldn't find it. I sent them an
I couldn't find it either, Dr. White. I was checking last night and I couldn't find them.
Oh no, it disappeared. It's a treasure hunt. No, not really. Good news, I wrote my own lab, if you notice. If you go to the assignment area, you'll see the lab today. I think it's lab 9. I might be wrong on the number. And lab number 9 is a fun lab. Let's go through it. Lab number 9 deals with the ideal gas law. And the ideal, oops, hold on. I always forget to do this. And I did. Thumbs up, people. Can you see the lab now? Thank you. All right. This you can download either as a Word file or as a PDF. And the ideal gas law is PV equal nRT. And remember, P is in pressure in atmospheres, V is volume, N is the number of moles, T is temperature in Kelvin, and R is the universal gas law constant. And for my class, I'm using this number, 0.0821 atmospheres liters mole K. Now, in chemistry, when you claim something's a law, it is always true, no exceptions. At today's lab, you'll find out, is it really true? Is the ideal gas law really a law? How do you do that? Well, by doing a chemical reaction and determining the volume of the gas formed at a certain temperature and pressure. From the ideal gas law, you can calculate the number of moles, N. And based on that, you know from the gas collected how many moles you had. And the reaction you'll be doing is this one. It's a cool reaction. Magnesium plus 2 moles, 1 mole of magnesium. Remember, the coefficient is molar ratios. 1 mole of magnesium reacts with 2 moles of hydrochloric acid. that's what HCl is, to make 1 mole of magnesium chloride and 1 mole of hydrogen. And as I taught you, and hopefully you'll remember for today's test, this tells us that for every 1 mole magnesium, you make 1 mole of hydrogen. So if you know the weight of the magnesium, you can calculate the moles of magnesium, because 1 mole of an element equals its atomic weight. So if I have grams of magnesium, I can divide it by the atomic weight and get moles of magnesium. Therefore, I know theoretically how many moles of hydrogen I have. So if the ideal gas law is true, the theoretical amount of hydrogen formed based on this reaction should also be equal to N in PV equal nRT in the ideal gas law, if it is true. I'm not going to give away the secret. You're going to have to figure that out for yourself. So if you know the pressure, volume, and temperature of the hydrogen formed, and using PV equal nRT, then you know the number of moles actually formed, N, which can be calculated. And if the number you get from the calculation of moles of magnesium equals moles of hydrogen is the same as N from PV equal nRT, then the ideal gas law is true. But again, Dr. White might be lying to you. The nice thing about chemistry and all science, you go into the lab and prove things. Is it really true or not? By getting something called facts. And by doing this, you'll find out is the ideal gas law. Now, let's do a neat little video. Hold on.
Illinois homeowners, if you have a
Time
colony
out
like
for
this inside your
commercial.
house, you can qualify to get solar.
Goodbye.
First thing you do in the experiment is measure the mass of the magnesium strip. There's an alternate way to do this that gives you more significant figures that's in the description. But for this particular experiment, we're really not going for intense precision anyways. In place, you need to kind of use a piece of copper wire, and you're going to put that through your 1-hole rubber stopper so it can kind of move in and out, but it's going to be stuck. And then you're going to put the magnesium in with the copper, but you need it to be held in place, because if it gets released during the middle of the experiment, it'll float up to the top and won't fully react. And so this can be pretty challenging. You have to be careful because you don't want to get a splinter from the magnesium, and then also it can be hard to position the thing correctly where it's actually stuck in there pretty well. Usually if you get some coils, you can kind of press the copper together. And if you're having trouble like I am right here, one of the things that you can do is you can grab
Not too coordinated, is
use
he?
that to really lock the thing into place. Just kind of give that a squeeze, and that'll hopefully hold it where it's not going to, as the bubbles go, rise to the top. Now let's go ahead and look at the UDiometer. So the UDiometer is open on one end and closed on the other.
We'll
You
use
pour
a
your hydrochloric
burette
acid
that
in,
has a valve
about
on
10
the closed
milliliters.
end.
And you want to use somewhere 3 molar to 6 molar hydrochloric. And it's also really important that you add food color to the hydrochloric acid so you can see it as you're doing the reaction. So I added blue food coloring, and the hydrochloric acid turned that into yellow somehow. So this has had a little bit of red added to give us an orangish color. And then you're going to pour just regular tap water in. And you want to
No, we use
pour it
DI
very
water.
slowly. So to do that, you need to tip the UDiometer, because what you don't want to do is you don't want the water and the hydrochloric acid to mix very much. You want it to kind of run down the side and form layers. And at the beginning, that's not going to work well, and that's fine. But by the point you get to midway up the UDiometer, that's going to change, where it's going to fill mostly with water. You can kind of see the color change as it gets higher and higher up. So it was a little little short on water, so now we're going to add just a little bit, and we're going to fill it all the way to the top so it's going to flood over, but it's not the hydrochloric acid at the top because it hasn't had a chance to mix evenly. So we're just going to let the water flow.
In our lab, you'd be wearing gloves.
With our one-hole stopper with a copper wire and the magnesium filled inside. We have the hydrochloric acid at the bottom, water at the top with the stopper. We're now going to flip that upside down. And as the hydrochloric acid, you can see that red color kind of moving down towards the magnesium. And what happens is, as that hydrochloric acid slowly mixes, it ends up reaching the point where it gets the magnesium. And when that happens, you start to see bubbling. And so as those bubbles go to the top, it pushes the hydrochloric acid mixture even further down, and the reaction continues to happen.
Takes a while for the HCl to go to the bottom.
See, this is going to actually start to react faster and faster. So right now at the beginning, you can see a little tiny bit of bubbling where the magnesium ribbon is, but that bubbling is going to pick up more and more and more as you see that red color shift down towards the bottom. So now we're going to go ahead and speed up the video so this doesn't take so long because it's a long stretch for this reaction to happen here. But we're going to flip
usually about 5 minutes in our lab.
See what's going on at the top as the bubbles push that water and hydrochloric acid as that gas is collected.
And before it started, you would have measured the top level, and I'll explain that in the lab. Those bubbles are hydrogen gas, H2. And notice the level the water is going down. That's because on top of it is hydrogen gas. We don't use copper wire, we use thread or string, and it works much better than this. Also, we have better holders than what he's using. And once it's finished, you'd measure the volume.
Slowed considerably. We're not quite done yet, but now if we take a glimpse of where we are, we can start to see if we're getting to the end. So currently we're between 62 and 64. It looks like we're right around 63 milliliters right now. So we're going to let this react a little more and see if that changes. It's 6 minutes later, and we've definitely changed from 63 right now. It looks like it's very close to 64. So when we look against the backdrop, it looks like it's just not quite to 64, so maybe 63.8 milliliters of gas that we've collected. Keeping in mind that the pressure is not even here because we haven't had the water levels evened out, and water temperature about 21.5 degrees.
When we do it, we measure the actual temperature of the room and the air because that's what the gas is above the water, not the water temperature.
This is a tomato.
Very
Think it's good
good.
for you? Think again.
One simple trick to controlling your weight. Cardiothoracic surgeon Stephen Gundry says he's solved.
That wasn't obviously part of the lab. All right, so you've seen how we do it, and I put in an experimental procedure how you would do it. Weigh and record the weight of the magnesium metal strip. Place the metal strip on the, I use their holder. We actually use a stopper like they do, but it has a string in it, a string that you wrap around a roll of the magnesium after you weigh it. You fill a beaker with the DI water. DI means deionized water. I'll teach you later on, there are ions in the water you drink when we get in farther into solutions. And then you add 10 milliliters of 6 capital M, you'll learn today or Monday, means 6 molar HCl solution in a burette. Then you notice the angle that, which you would do, slowly add the DI water. So you have it all the way to the top of the burette, put the metal strip in, put the stopper in, put your glove finger, because you'd be wearing gloves and safety goggles in the lab, invert it, put it in the water. Measure immediately the initial volume, because we're using a burette, not what he has. So there's a little gas on top to begin with. Then watch the bubbles form by reacting with the magnesium. Those bubbles are hydrogen. When no more gas is formed, measure and record the volume of the water that's in the burette, just like a graduated cylinder, which unfortunately I talked about a while ago, but you don't have hands-on experience. And then what I would have you do is you'd all have your own thermometers, and you could measure the temperature in the room. In each lab, we have a barometer, and I'd ask one student to look at it and tell what it is. And I'd convert it into millimeters of mercury or torr, because it's usually in inches of mercury, which is what we use for weather. And then I'd have you dispose of the liquid in the burette in the beaker in a white waste container and rinse out and clean your glassware. Now, data. Here's the weight, if you were in a lab, what you did for the metal strip. Here's the initial volume of the water in the burette. Here's the final volume. The volume in milliliters form is 3 minus 2. So you now have the volume in milliliters. Temperature in Celsius, centigrade, Celsius, I got it right. The old name was centigrade. Atmospheric pressure, which is also the pressure of the gas in the tube, is this, 755 torr. Now, here's some calculations. Moles of magnesium used. And that is, you should know, you figure it out, the weight divided by the atomic weight of magnesium. This you can find on your periodic table. Now, based on the chemical reaction, every 1 mole of magnesium makes 1 mole of hydrogen gas. Once you calculate the moles of magnesium, number 5 here, you have the same number of moles of hydrogen produced, number 6. Now, temperature for PV equal nRT has to be in Kelvin, so the temperature above in degrees C, you add 273, and you get temperature in Kelvin. Now, calculate the room atmospheric pressure, and you have torr. Remember, 1 torr equals 1 atmosphere. Use your good buddy, your good friend, unit analysis to do this. If you have problems doing this, come to my office hours Monday night. I'll help you out, but you should be able to do this. I did this calculation already in class, actually in Zoom. Next, pressure in atmospheres. Well, the room temperature, room pressure in atmospheres is the same as the hydrogen gas. And the room temperature in Kelvin is the same as the hydrogen gas in Kelvin. Now, for PV equal nRT, and I'll never do this on a test, but in the lab, you measure milliliters, not liters. So how do you convert to liters? You take number 4 and divide it by 1,000, and then the volume of the gas, number 10, will be in liters. Now, number 8, I'm going to make you work a little. Dr. White's mean today. Moles of gas form, you have to calculate that using PV equal nRT. Solve for N, I've taught you how to solve for one thing on the side. Remember, the universal gas law constant R is 0.0821. Now, besides the calculations, here's some questions. How many moles of magnesium metal were used? You did that in the calculations. How many moles of hydrogen theoretically were used using your balance equation. Hint, your question number 1 answer. How many moles of hydrogen were made using the ideal gas law? Your calculation number 8. Boy, I'm making this too hard. And did you prove PV equal nRT? If so, how do you know this? I'm not going to give that away, but I should tell you, if N both ways is within 20% of each other due to the really expensive lab equipment we're doing, it's equal. Again, you're not going to get the identical number. I couldn't even do that. All right, any question on the lab? Again, this is due Tuesday because today's Thursday. By the way, I forgot to do this because I've been rushing today, so I better do this. And that is, good morning, everybody. Hopefully you're ready for another sunny, exciting day of Morning of Chemistry with me, your host, Dr. White. That always gets me in a good mood. All right, any question on the lab? Got my volume on my speaker's on so I can hear you. Check to see nobody's doing a question in chat. So let's continue. Thumbs up, people. Can you see chapter 12? Thank you. All right, just to remind you, when we talk about solutions, you can have a solvent, only one solvent, that's the component present in the greatest amount. You can have many solutes, those are all the other components in a solution. Right now I'm drinking tea, the solvent is water, and all the other things that make tea taste good, plus the sugar I put in there, are solutes. And I talked about different solutions, about the solubility factors, types of solutions you should know. Saturated solution, you have the maximum amount of solute dissolved in the solvent. You can't put one molecule more, or guess what? It will dissolve. Dilute solution, you have a small amount of solute compared to what you could put in. I'm going through this quickly because I talked about it yesterday. Concentrated solution, you're not at maximum saturated, but you're pretty close. You have a large amount of solute present in your solution. This is really important. Aqueous solution tells you that the solvent is water. Non-aqueous solution tells you the solvent is anything but water. And this I said switches off. Same thing here. All right, now, hold on. This is probably one of the most important things I'll teach you for your daily life this whole semester. And that is, I don't know why this is here. And that is the concept like dissolves like. And what this means is substances of like polarity tend to be more soluble, and really not more, are soluble in other substances that, this is wrong. I don't know how this got messed up. Let me do my own thing. Don't look at this. I think I have it here. Things that are polar are soluble in polar things, and things that are nonpolar are soluble in nonpolar things. All right, now it's right. Things that are polar, meaning compounds, are soluble in polar solvents. Things that are nonpolar are soluble in nonpolar solvents. When you try and mix something that's polar with something that's nonpolar, it's not. Now, like dissolve like is not a law. It's called a rule of thumb. See, it's on, wait, it's on this thumb. Can you see it? And a rule of thumb is about 95% true most of the time, but not like a law, which is always true. In a rule of thumb, there are exceptions, but most of the time it's true. And like dissolve like is a very important concept. That's why, how many of you have ever seen oil vinaigrette dressing? You know, in a bottle, you shake it up, you put it on your salad, you put the bottle down. What happens? It separates. Why does it separate? Like dissolves like. Now, how many of you have ever washed your hands with soap and water to get your hands clean? I hope all of you have, especially with what was happening in our society and our world right now. And soap works on the principle like dissolves like. If you take my organic chemistry class, which I'm teaching at Elgin Community College this fall, I don't teach it here anymore. I won't go into that story. I used to. And, oh, see how much of a hurry I was in? Now I look better. But I teach about how soap works and other things with like sounds like. If you need organic chemistry, since it's going to be totally online, they're going to announce it after the 20th. Why they're waiting so long, I don't know. It's already been approved, but I'm teaching it here. You have to go into a lab to do it as COD, meaning here. But let's look at like dissolves like. All right, like dissolves like. I hope I spelled dissolves right. But anyways, first thing you should know, what are polar compounds? Most polar thing in our world is water. Alcohols are polar, like the alcohol you drink, the alcohol in rubbing alcohol. Also, all salts are polar. Ammonia is polar. Salts like sodium chloride are polar. Now, what's nonpolar? And this is something you should know. I'll debate whether or not I give this on test number 3. Well, important things that I won't talk about in this class, but dirt is nonpolar, which is why you can't wash it off your hands with just water. Also grease. Vegetable oil. And let's do a couple others. Baby oil. Why did people put baby oil on the baby's certain parts? Because it keeps moisture off, moisture from their diaper. Because like dissolves like. But you never thought Dr. White would get into diapers. Well, in the lecture. I shouldn't have said that. Ouch. And let's see, what's another one? Vaseline, otherwise known as petroleum jelly. And one more, gasoline. And if you take water and sodium chloride, it will dissolve. Why? Like dissolves like. If you take sugar, which is an alcohol, you don't know about that. It's not the kind of alcohol that gets you inebriated. but sugar is an alcohol and it dissolves in water quite well because of like dissolves like. Now, years ago, I was teaching Chem 1211. I had a very good student. He's real sharp. And that student liked to ask a lot of questions, which made me happy because there's no such thing as a dumb question. And that student, after I just said this, remember, things that are polar are soluble in polar things. Things that are nonpolar are soluble in nonpolar things. You try to mix the two together, that won't happen. And the student raised his hands and said, Dr. White, well, if like dissolves like is true, can I dissolve Vaseline in vegetable oil? I said, I don't know, I've never tried it, but I believe in like dissolves like. So next time we had a lab, in the lab, I got from the stock room of the lab some vegetable oil, which we had, and Vaseline, gave it to the student. I asked him first, do you mind doing a demonstration for the class? He said, no. So I gave it to him with a beaker and said, well, mix the two together in a stirring rod and let's see if it dissolves. And lo and behold, it did. This is soluble in that. Why you'd ever want to do that, I have no idea, but like dissolves like. I'll be done in a second, maybe more than a second. Let's try again. It's easier on a whiteboard in class. It's supposed to be a question mark. That. All right, let's look at this. 5 points. A compound A is soluble in water, but not in vegetable oil. Compound B, and I'm missing a D there. Did I tell you I was always the first one down in a spelling bee? I was. Compound B is soluble in vegetable oil, but not in water. What are the polarities of A and B, and how do you know this? I'll let you think about that for a little while. I'll give you a whole minute because I'm going to drink some tea. By the way, if you can't see above or you didn't take notes, water is polar, vegetable oil, non-polar. At this point, I'd be telling the class, if I were standing in a class, when you're done, look up and smile. But with this class, when you're done, give me a thumbs up. All right, I see thumbs up. I'll give you another 10 seconds. I gave you more than 10 seconds. All right, how do you do this? Well, you look at this and say, give me a little more room here. As I told you, water is the most polar thing. Vegetable oil is non-polar. That's why oil vinaigrette, vinegar is mainly water. When they say oil vinaigrette, they're talking about vegetable oil. If you have made your own, you should. Tastes better than anything you can buy in a store, but that's another story, another day. And therefore, because of light dissolves light, I know A is polar because it's soluble in water, but not vegetable oil. And B is nonpolar. And this is one of the most fundamental principles I've worked with in organic chemistry in areas I worked in that have helped me by understanding light dissolves light and knowing water is polar, so is alcohols, so is salts, so is ammonia. Nonpolar, dirt, grease, baby oil, Vaseline, gasoline, vegetable oil. Speaking about gasoline, how many of you ever been in a gas station after it's rained? Wow, how you like that? Rained. That was pretty hokey. But you look around and you see little puddles of water. And if you see the sun come out and hit the puddles of water, and if you're standing right, you see like a film on top that looks like a rainbow. How many of you seen that? I hope some of you have seen it. It's real pretty. And why is that happening? Well, it turns out if you've ever been in a gas station, you can always see someone spilling some gas on the surface, whether it's cement or asphalt, underneath their car. And that stays on there. Eventually it'll evaporate away. I'll teach you later on what evaporation is. But if it doesn't and it rained, now you have water. And because water is polar and gasoline is nonpolar, they don't mix. So you have the gasoline on top, the water underneath, and when the light hits it, it refracts it, and like a prism separates it into different colors of the rainbow. So the next time you're in a gas station after it rains and you see a puddle of water and the sun come out, and you see those pretty colors on top, and you're with a good friend, you say, you know, that's because the light dissolves light, because gasoline is not soluble in water. People don't like hearing chemistry in gas stations. All right, let's move on. This is not on the test, but how does soap work? They're called surfactants, which is short for surface active agents. Dr. White has about 6 patents, US patents, dealing with surfactants. So it's an area I'm a world authority in. And those are chemicals that have a polar and nonpolar end, and they help interact water with things that are nonpolar, like grease and dirt. And that's how soap works. And things that have surfactants, your hand soap, your laundry detergent, your shampoo, They all work like that. So the next time you're washing your hands, washing your hair, washing your clothes or your dishes, because a like dissolved like, it's getting clean. I won't put that ever on a test. And you've got that on video that I'm saying that. All right, an important part of solutions is called concentration. If I could turn the switch that only goes to 10, I've just turned it to 30. In other words, this and the next couple of slides. I'll tell you what's important, what's not. Isn't it nice Dr. White can be subtle? Hint, know this. All right, when we're talking about concentration, that's the amount of solute present in a specific amount of solution. Now, if I were to ask one of you, quick, go into the lab or your kitchen, since you're not at COD, and why don't you mix together some sugar and water and make me a sugar solution? Put some sugar and water, mix it up, you're done. Well, if I asked 4 of you to do that, would you all do the same thing? No, you'd make different solutions. All of them have water and sugar, but how much water, how much sugar would make a big difference, like how sweet it tastes. More sugar, less water, the sweeter it would be. So this is called concentration. It's a very important concept in solutions. Now, there are different ways of measuring concentration. Now, one is by percent mass. For this slide, I'm turning the switch. Will this be on test or final? Off. But this is something you should know for your daily life, so I'm going to tell you about it. Now, percent concentration by mass, or sometimes it's called percent concentration, is the mass of the solute divided by the mass of the solution times 100. And the mass of the solution is the mass of the solute plus the solvent. The higher this number means the more solute is present in the solution. And if you ever go buy something, hold on, Dr. White has to go get something. Hang in there, I'll be right back. I'm back. I had to go all the way down to my utility room, down 2 flights of stairs, and I'm back. Anyways, you were worth it. Years ago when I bought the house I'm in, first time got warm out and I'm mowing the lawn early, guess what happened? I got attacked by mosquitoes. That wasn't fun. So I went to the local big box store, in this case, Walmart, and I went to where they had the mosquito repellent. And they had the name brand off, and they had this, their brand. And on the back, you can see, or on the front actually here, it says DEET 40%. DEET is the molecule, because I'm an organic chemist, I know this now, you do, that helps keep the mosquitoes away. They just don't like the smell of it. Well, the more DEET, the better it is. Well, anyways, they had this bottle for like $3 and the name brand $6. The name brand had a little less, and the amount of DEET, that 40%, that's percent mass, was only 30%. So let's see, do I pay less money, get more of the liquid, and have more of the stuff that actually keeps the mosquitoes away because it's cheaper? And the answer is yes. And I've been using it ever since. I don't buy the off. By the way, I don't get any payments from Walmart or off to make a commercial. But when you look at labels, look for the active ingredients. And if you're looking at two products, look at them, and you now know percent mass. When they say percent here, they just say DEET active ingredient 40%. That means percent by mass. The higher the number, the more of that in there. And the more in there, the better it is. Another thing that happened a number of years ago, we had a heavy rainstorm, and I had some seepage through a crack in my wall in my utility room. Not much, but enough. And it started not smelling well. And I know that was because probably there was mold in that crack. And so I went, because I'm an expert in, it's called quaternary ammonium salts that actually disinfect things. And I have patents in that too. It helps to know things in organic chemistry. And I went, and they had those spray cans where you can buy the disinfectant, and they have quaternary ammonium salt in there. And I know the names of the key quaternary ammonium active ingredient. It has a long name at the end, the word chloride. And the Clorox brand had 5%. The Walmart brand had 8%. The Walmart brand, same weight as the Clorox spray can, was less money. So which do I buy? Not the name brand, their brand, because it's cheaper and it has more active ingredient. I sprayed it on the wall, and within a day or so, it didn't smell anymore because it killed all the mold from the moisture that hadn't dried out. Now you know percent mass. That won't be on the test, but I thought for your daily life, you should know that. Next, switch is still off. Will this be on test? No. Another way of doing concentration is by percent volume, and that's the volume of the solute divided by the volume of the solution. The volume of the solution, which I don't have on the slide because you're never going to calculate it anyways, is the volume of the solute plus the solvent. Where do you see this? On bottles of wine. They'll normally give you the volume of alcohol to the volume of, or percent volume alcohol, which is calculated here. The higher the number, the more alcohol, and the stronger the wine is. But the most important thing is this, and I've just turned the switch up to 100. This is one of the most important concepts in chemistry when you're talking about solutions, and that's molarity. Molarity, which is abbreviated by capital M, of a solution is a ratio giving the number of moles of solute per liter of solution. By definition, molarity, moles of solute per 1 liter of solution, and it's shown by a capital M. In the past, I used to make the students memorize this. That will be given to you on test number 3. Now, since 1 liter equals 1,000 milliliters, moles per liter equals moles per 1,000 milliliters. And this is a better definition that I like to use. And this, when I write IMP with a bunch of stars after that in my notes when I was a student, like this, that meant you better know this. And this is very important. Molarity equals moles of solute per 1,000 milliliters. Come on. And the question is, and let me just do a quick thumbs up, people. Can you see what does, thank you. All right, what does 1.75 mole, capital M, HCl mean? Good question. Whenever you see capital M, that means molarity. And you should know that's moles per 1,000 milliliters. And that's solute. Therefore, what does this mean? It means 1.75 moles HCl per 1,000 milliliters. Your turn. You try that. Give you 10 more seconds. Bonus time. Time's up. As soon as you see capital M, that means molarity. And what does this mean? It means 2.01, capital M means moles of solute, sodium chloride, per 1,000 milliliters. Now, there's something else you should know. And what does 2.33 capital M NaOH bracket AQ close bracket mean? And what is the solvent? Well, first of all, this tells you 2.33 capital M, molarity, moles solute, in this case, sodium hydroxide. You'll learn later this semester what is sodium hydroxide per 1,000 milliliters. If you put liter, that's okay, but in our calculations, this is more helpful. And what is the solvent? Bracket AQ close bracket tells you the solvent is water. Whenever you see AQ in a bracket, aqueous, that's shorthand or abbreviation, that tells you the solvent is water. I'm going to go another 5 minutes because I started late. I apologize for starting late, but I think I want to get to this. And the question is, 6 points, how many moles sodium chloride are in 151, that's the number 1, milliliters of a 3.33 capital M NaCl solution? So what are we trying to find? Moles sodium chloride. What are we given? 151 milliliters of solution and this strange number, 3.33 capital M NaCl. Now, first thing I like to do is, oh, capital M, molarity. What does that mean? That means 3.33 moles sodium chloride per 1,000 milliliters. Now, what do I have to really work with? This, 151 milliliters. What if I had a conversion factor ratio? What units do I want my answer in? Moles sodium chloride. And guess what time it is? It's time for your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the units go on top. Whatever we're trying to get rid of, the units go underneath. Therefore, this would be moles sodium chloride. This would be milliliters. Where do we get these numbers? From knowing that molarity is moles per 1,000 milliliters. In this case, 3.33 per 1,000 milliliters. This is an exact number. This is 3 significant figures. This is 3 significant figures. So our answer should be 3 significant figures. Notice anything divided by itself equals the number 1. Milliliters divided by milliliters cancel out. I'm left with the units I want. Hang in there, I'm almost done. Two days later, he's almost done. Wow. Hold on. That's better. And if you notice the number, that would be rounded off 5.03 times 10 to the minus 3 moles of sodium chloride. You could put this number down. I just rounded off 3 significant figures. Keep the 5, keep the 0, keep the 4. 8 to round off, that's 5 or higher. That gets dropped, and the 3 just gets moved up to a 3. And the answer here would be 5.03 times 10 to the minus 3 moles. And that's how you do it. Sorry I went over. Sorry I was running late by a minute or two. It's time to say goodbye. Really goodbye. Have a great week and weekend. Don't forget, test number 2 is due tomorrow. Also, the Labster lab, nobody can find it, disappeared. I left them a note last night. Where did it go? I haven't received an answer yet. I also left them a note because you give me the email of your CEO, so I'd like to talk to him. I don't think I'll get it, but I thought I'd ask. But everybody, gang gesund, be safe. I'll see you on Monday. By Sunday latest, hopefully earlier, I'll have your test number 2 scores in Blackboard. I'll send out an email. I'll also, before Sunday, send you an email with individually each of your individual points for each answer you put on the test. And on Monday, I will go through the test. Also, Monday, I will go through the gas law problems. Next Wednesday, I'll be going through the solutions problem because I'm almost done with solutions. We're on track. Like I said, I'm picking space up, but I always do that. If we're in the spring, you'd see me doing it. In the summer, it just seems faster. With that, bye.